Okay, so in this video, we will consider two examples of a removable discontinuity. So a given value of x where the given function is not continuous, and you'll understand why we use the word removable, simply because we can remove the discontinuity by redefining the function at the given point of interest. So here's our function. So here's our first example. Suppose we consider f of x to be the following rational function, x squared minus 1 over x plus 1. As we have said in the previous video, all rational functions are continuous on their domain, and so the only value of x where the function f may be discontinuous is at a point where the function is undefined. Well, both polynomials are always defined, but there is a division here, and the one thing we cannot divide by is of course 0. X plus 1 is 0 and x is negative 1, and so we must check here the point negative 1. So this is a possible discontinuity, and if we try to evaluate f at negative 1, let's see what happens. Negative 1 squared is 1, minus 1 is 0, over negative 1 plus 1 is 0. And of course 0 over 0 is undefined. So right away we know that the function f of x is discontinuous, not continuous at x 0 equals negative 1, because the function is not even defined there, right? If you remember, we only have continuity at a given value of x if and only if the limit of the function as x approaches the point of interest equals the value of the function at this very same point. So the implication again is, for f to be continuous at x0, f of x0 must exist, the limit of f as x approaches x0 must also exist, and they must be equal. Here, f of x does not exist, so right away, x0 being negative 1 is a point of discontinuity. This was simply a reminder again of continuity. So f of x0, f of negative 1 is undefined, so negative 1 is a point of discontinuity. Okay, I claim that this should be called a removable discontinuity. Well, let's see. We've already figured out that f of negative 1 is undefined. What about the limit? Let's see if this exists or not, and if it does, what we can do about it. So now we are letting x approach negative 1. Let's see what kind of limit we're dealing with. F of x is x squared minus 1 over x plus 1. As always, when we have a limit, we consider the case that we're dealing with. Well, as x approaches negative 1, x squared minus 1 approaches 0, and x plus 1 also approaches 0, so we have an indeterminate form as a 0 over 0 case. But we know that both polynomials are equal to 0 at negative 1, and so x minus negative 1, therefore x plus 1, is a factor of both polynomials. Well, this is trivial here, but we can factor our numerator. And of course, x squared minus 1 factors as x plus 1 times x minus 1. Now, as x is approaching negative 1, x is very close to but not equal to negative 1, and so x plus 1 is not 0, and so we can cancel the common term on top and on the bottom. And now we are left with a rather trivial limit. As x is approaching negative 1, x minus 1 will approach negative 1, which gives us negative 2. And so you see the limit of the function as x approaches negative 1 does exist. The only problem here is the function is undefined at negative 1. Let's graph this and see why we may classify this discontinuity as removable. And let's actually explicitly write the function. Right? F of x, as we have just seen, is equal to, as long as x is not negative 1, we can factor x squared minus 1 as x plus 1 times x minus 1 and cancel the x plus 1 term. So the function is simply x minus 1. Of course, as long as x plus 1 is not 0, and so as long as x is not equal to negative 1. So for any value of x aside from negative 1, our function is simply the linear function x minus 1. And as we have already seen, if x equals negative 1, the function that gives us 0 over 0, which is undefined. So the function is actually quite simple, right? It is always y equals x minus 1, except that there's a hole in our function. At x being negative 1, there's no value. So let's look at this graphically. The point, of course, of interest being our point of discontinuity, negative 1. So we'll draw look first at the value of interest. X is negative 1. And we know at this point there is no value, but everywhere else the function is x minus 1. So we'll graph x minus 1, but we'll have to leave a hole around x being negative 1 as there is no y value for this function. Well, at 0, the value is negative 1. And, of course, at x equals 1, the value will be 1 minus 1, which is 0. So we draw the line y equals x minus 1, except we know that at exactly x equals negative 1, there is no y value. So there is a hole in our function. I'm exaggerating, just so we're clear on that. The function for any value of x but negative 1 is always the line y equals x minus 1, except that there is a y value missing, specifically the y value when x is negative 1. But, as we have previously found, the limit of our function, as x is approaching negative 1, is negative 2. And so the y value here is negative 2. Now let's see why we may call this discontinuity a removable discontinuity. Think of it as, could we fix the problem, therefore remove this discontinuity so that the function becomes continuous at x equals negative 1? And the answer is yes, right? What if we define, we're missing a y value for x being negative 1, what if we define the y value at negative 1 to be negative 2? Then we are going to fill in the missing value and the function becomes continuous. So we let f of negative 1 to be defined as negative 2. If we do so, then we have a y value at x equals negative 1 that fills in our hole, the missing value, and now the function is continuous. So whenever you have a simple hole in your function and you can remove it, the discontinuity is removable. So x0 equals negative 1 is a removable discontinuity. And that's it. So you'll see that when you have a removable discontinuity, the limit of the function will have to exist, but the function will simply be undefined at the given point. So there'll be a y value missing. Let's do one more example of a removable discontinuity, one that is slightly more interesting. Here's the function, so f of x equals the root of x squared plus 7 minus 4 over x minus 3. Now this is a power function over a polynomial. This is one of our familiar functions, and so it is continuous everywhere in its domain. Well, where is the function undefined? There is a square root, so we have to watch for negative arguments, but as it is x squared plus 7, this is always positive, so our numerator is always defined. So is our denominator, as it is a polynomial, but there is a division. And so the one thing that we have to avoid is a division by 0. So here, we have to check the value of x being negative 3. And this is the only possible point of discontinuity of our function. So first, let's look at the value of the function at this point. So f of x0 being f of 3. Well, 3 squared is 9, plus 7 is 16. The root of 16 is 4, minus 4 is 0, over 3 minus 3 is 0. And so, as in the previous example, the value of the function at the given point, x is positive 3, of course, not negative 3, right? If x minus 3 is 0, x is positive 3. So this is undefined. Well, so we already know that because the function does not exist at this point, that x0 equals 3 is a point of discontinuity. Well, let's see if it is indeed what I claim to be a removable discontinuity. Let's consider our limit as x approaches 3. Our function, of course, is the square root of x squared plus 7 minus 4 over x minus 3. As always, when we have a limit, we consider the case that we're in. As x approaches 3, x squared approaches 9 plus 7 is 16, root of 16 is 4 minus 4 is 0, and obviously as x approaches 3, x minus 3 also approaches 0. And so we have a 0 over 0 case. But if you remember we have a 0 over 0 case, what's interesting here is that there is a difference involving a square root. And so to solve this limit, to figure out what happens, we have to use the method of conjugation. Now if you remember, the conjugation is we multiply top and bottom by the exact same expression involving the difference with the square root, but we change the sign. As we have a negative, we will use a positive now. This is of course legitimate, as we are multiplying top and bottom by the same expression. All this is a strange way of multiplying by 1. The idea next is to multiply the square root and the difference with its conjugate and to leave the denominator alone, as if we multiplied these two terms out, we would gain no simplification. But if we do the numerator, we'll get x squared plus 7 plus 4 times the square root minus 4 times the square root is 0, minus 4 times 4 is minus 16, over x minus 3 times the root of x squared plus 7 plus 4. But if you notice on the numerator, we get x squared minus 9, which factors as x minus 3 times x plus 3. And now we're almost done. As x is approaching 3, x is very close to but not exactly equal to 3. So x minus 3 is not 0, and we can cancel the common factor on top and on the bottom, and we're left with a very simple limit. As x approaches 3, x plus 3 approaches 3 plus 3, which is 6, over 9 plus 7, 16, root of 16 is 4, plus 4 is 8. We can simplify. 6 over 8, common factor of 2, is 3/4. And so our limit does exist. So let's write down what our conclusion is at this point. We have just verified that the limit of our function f of x, as x is approaching 3, equals 3/4, but f of 3 is undefined, as it gave us 0 over 0. So we can once again look at this very simply graphically to get a feeling for what this looks like. Now graphing this function is obviously a little bit more complicated, so you'll simply have to take my word for it, at least around the point of interest being positive 3. So f of 3 is undefined, there is no value, but we know that when x is really close to 3, the y values f of x are very close to 3/4. So there's a hole at 3, f of 3 doesn't exist, but as x is really close to 3, as I've just said, f is really close to 3/4, and the function happens to be increasing. So we'll simply graph it around this point, and it looks a little bit something like this. I'll exaggerate the behavior, but it looks something like this. And if you notice once again, yes, there is a discontinuity, there is a break in the function, as there's a hole at x equals 3. But once again, we can fix this if we now define f of 3 to be 3/4. If the y value at 3 is 3/4, then we're filling in the hole, which again I exaggerate, and now there is no longer a break in our function, which makes it become continuous. Because we can fix the problem this way, x0 equals 3 is also a removable discontinuity, because we are able to remove it. And that's it. So to summarize very shortly, to have a removable discontinuity, two things must happen. The value of the function at x0 is undefined. So there is no y value at x0, but the limit of the function as x approaches x0 exists. The value could be, as we've seen, negative 2, 3/4, 7 over 9, doesn't matter. But if the limit of the function exists around x equals 0, but f of x0 is undefined, this implies that everything is nice except there is a hole in your function, and if you fill in the hole, you remove the discontinuity, so this implies that x0 is a removable discontinuity. And that's it.